Igor, get down here.
It's Gregor, Dr. Wolfenstein.
Listen to me, Groupon. I've had a breakthrough.
Another one?
It turns out I've been piddling away my genius on these rinky-dink experiments. I'm going to put Piers Morgan's brain into a Komodo dragon.
That one was especially messy.
Why didn't somebody tell me that isn't where the action is? Why didn't you tell me, Enron?
I'm not sure what you're saying, Dr. Wolfenstein.
Black holes, you chump wagon. Do you know how hot it is inside a black hole? Like 10,000 degrees Kelvin.
My name is Gregor.
No, Kelvin is... I can't get sidetracked. If I'd taken up black holes last year, do you know where I'd be right now? Stockholm. Beautiful, magical Stockholm. Where stockings were invented.
Actually, I don't think that's...
I could be sitting alongside a canal sharing a herring liqueur with that dreamboat Michio Kaku, but where am I instead? Stuck in a basement full of 50-year-old equipment, talking to a hunchback.
Actually, Pilates is really helping my posture.
I'm going to make a badass black hole. First, I need a supernova, but not just any supernova. A champagne supernova.
In a champagne supernova, a champagne supernova in the sky.
Man, Oasis was so great. I really regret turning them into flies. I'm getting off track again. I'm going to make a black hole, and I'm going to collapse it so that everything is crushed and incinerated except anybody who doesn't go in the black hole, and those people will be stuck outside the universe.
And then what?
And then what? And then I smack you in the head for asking, and then what? Which you do all the time. And we both know I'm not good at end games. Jeez, I'm crow. And then what? And then what?
If you're going to collapse the whole universe, it just seems irresponsible not to...
No, that's the whole point of a black hole. Infinite gravity, infinite density, all of which is collected at a point that occupies no space at all. How's that for and then what? Now go buy some champagne. Use the money we got from the Knight Foundation. They never audit us. I wish I was in Stockholm right now, just for the thrill of not breaking up the fistfights. It's time for the rest of you to learn about black holes. And now he's often described as the next Einstein, the next Zeppo Einstein, Colin McEnroe.
Well, Zeppo Einstein is really one of the overlooked Einstein brothers. Albert gets all the attention. But in fact, there has been a conference going on in Stockholm where there has been quite a bit of controversy, because there's always controversy about black holes. Black holes are still not yet, as you will learn today, a static theory, a settled question. They're pretty much the opposite of that. So in ways that we hope that you can understand, which will be judged by whether I can understand them. I'm a good canary in the coal mine for this kind of thing. We're going to talk about the history of black holes, the history of at least what we have thought we've known about black holes. We're also going to talk about the way they're represented in popular culture, and we're going to tell you the current state of thinking about black holes, which, as I say, is the proverbial moving target. It really does change pretty frequently. And in studio with me, speaking of the next Einstein, Nikodem Popławski. He's a theoretical physicist. He's also a senior lecturer and physics coordinator at the University of New Haven, and he was prominently mentioned in a national publication as on the short list for being the next Einstein. So take that. I mean, it doesn't get any better than that. Also joining us is Marcia Bartusiak. She's an award-winning author and professor in the practice of science writing at MIT. And her new book is Black Hole, How an Idea Abandoned by Newtonians, Hated by Einstein, and Gambled on by Hawking became loved. She joins us from a studio in MIT. A little bit later, we will talk to Andrei Bormanis. He's worked as a special consultant to Star Trek Voyager, lots of other Star Trek-related, I shouldn't say enterprises, lots of Star Trek-related spin-offs and some feature films as well. He is a he tries to make sure that they get the science right, particularly when they're talking about things like black holes. So that sets things up for you. We're going to begin because, in fact, I'm not sure everybody walks around with any kind of thumbnail idea of what a black hole is. So, Nikodem Popławski, you imagine that you're at a cocktail party, and without getting into your particular theory, your relatively new theory about black holes, which we will discuss as the program rolls along, but just in terms of sort of what, if you said, well, one of the things I study is black holes, and I said, we're both at a cocktail party, oh, I don't really know what black holes are. In that informal context, what would you be able to say to me to kind of help me understand the subject?
A black hole is the region of space from which nothing, even light, cannot escape. This would be probably the simplest definition of a black hole.
So it's a do we know what a black hole is made of?
What do you mean bit of?
Well, made of, like what's in a black hole? Yeah.
Oh, we do not know that because we are residing outside massive stars or centers of galaxies which make black holes, and what we can observe is the motion of matter to the boundary of a black hole, and what happens inside we can not know unless we go into a black hole.
Right. And so the other question that goes with that, and you've implicitly answered it already, is have we ever seen a black hole? Has anyone ever seen a black hole?
Technically, we do not see black holes. What we see is almost black holes. We see black hole candidates because the formation of the event horizon, which is the name for the boundary of the black hole, happens in our frame of reference after infinite time. So the black holes are almost there, but not yet.
All right. One way that I saw it described that was helpful to me, I don't know whether you'd go along with this, is that in terms of the event horizon, it's almost like where a waterfall forms. And if you think about the water that's near the edge of where the waterfall forms, there's a certain point in that water where you couldn't swim out of it, right? You wouldn't be able to swim away from the waterfall. You're just going down into the waterfall. And then as the waterfall falls down, it also there may even be water kind of splashing up, so you'd be kind of caught between those two things. Is that reasonable?
Yeah, it is a nice analogy. Event horizon is like a unidirectional or one-directional motion surface. You can go in, but you cannot go out.
All right. And well, as we one of the questions is, what, if anything ever does come out, is information lost in a black hole? That's one of the things that was being debated in Stockholm last week, and we will talk about that too as we go along here. But I think it's time to, in fact, add Marcia Bartusiak to this conversation. Marcia Bartusiak, one of the reasons that we wanted to have this conversation, part of it was because we read about Nicodem in an article that was, I believe, occasioned by the 100th anniversary of the theory of relativity. So the question was, who's going to be the next Einstein? Well, it might be him. But the truth is, reading your book, focusing on Einstein is both relevant and not 100% relevant. And really, that's 100 years ago, but really this conversation starts maybe like 250 years ago, right? In the Newtonian world, there were still scientists thinking about whether there could be points in space from which light does not emit. Do I have that right?
That's exactly right. Physicists like to think of extremes because it tests their theories. And there was this 18th century scholar in England named John Michell, who decided to take Newton's law of gravity to the extreme. And he imagined, what if I had a star that was 500 times wider than the sun and just as dense throughout? At that point, he calculated by Newton's law of gravity, the gravitational field would be so strong that if a light particle tried to go out, radiate from the star, it couldn't get out. He was using the analogy that light were like particles of water coming up from a fountain. It would go up to a certain height and then fall back because of the strong gravitational field. He had the wrong theory of light, and he had the wrong theory of gravity because it doesn't work in that situation. But it was the sort of Model T version of a black hole. It was the first time that scientists thought about the possibility that there could be this dark pinpoint on the sky from which we couldn't see any light from the star.
And oddly enough, almost simultaneously, there was a scientist in France, in Paris, I believe, doing pretty much the same kind of thinking, although he didn't stay with it maybe quite as steadfastly as your friend Mitchell did.
His name, he's the mathematician Laplace, who independently did the same calculation. It's something that scientists like to do. They like to imagine what is the biggest, brightest, strongest, and they worked out that calculation. But John Mitchell did it first, and he actually had a better understanding of it than Laplace.
We're going to skip ahead just because we can't walk. The book, by the way, is fascinating, and it's really, for somebody like me, which would be somebody who doesn't understand this stuff, it's as close as I've gotten to understanding some of the ideas of relativity that are crucial to understanding this subject. So we'll have to skip over big chunks of the book. Although one thing I do want to say as we get to Einstein is that although Einstein's theories are important to relativity, my sense in your book is that this man Schwarzschild is really the guy who kind of takes Einstein's stuff and makes black holes out of it.
Well, exactly. Einstein did not introduce the idea of the black hole. His equations were very, very important for developing the modern idea of the black hole. But it did come out of just a couple weeks after Einstein introduced his theory in 1915. Karl Schwarzschild, who was then, this is something, he was on the Russian front with gunfire nearby, but he's so excited. He is a German astronomer who was serving his duty during World War I, but he kept up with his physics work, and he had Einstein's paper in hand, and he came up with the first full solution to Einstein's equations of general relativity. And out of that came this problem that really flummoxed him. He saw that if he collapsed all of the mass of a star, say the sun, into a point, he did this because it made the mathematics simpler. He noticed that there was this region, the spherical region of space that arose, where when he threw particles at this imaginary point, there would be this area in which time stopped, the particles stopped. In fact, the particles vanished. He didn't know what to make of it. In his report in 1916, he just says it wasn't physically meaningful. It was just a mathematical game. No one believed stars were ever going to do that. But it was the sort of first hint of the possibility of black holes. And in 1916.
So there's sort of a paradox. And by the way, poor Schwarzschild, he then dies of this horrible disease, right? There's sort of a paradox here, Marcia, which is that this is very much a moment in the Einsteinian revolution. On the other hand, it's not something Einstein's super comfortable with, right? By 1939, he's trying to get rid of black holes.
Exactly. He, along with Schwarzschild, thought that this really wasn't the way nature worked, that you didn't have to worry about it because no star was ever going to collapse to a point. At this time, with their knowledge of astronomy, the universe was quiet and serene. It didn't have crazy violent effects. Stars didn't do these crazy things. So they just didn't worry about it. They just thought of it as just a sort of mathematical puzzle that didn't have anything to do with the real world.
You know, Nicodem, I want to just talk about the reading Marcia's book. It's clear that astronomy is two different things, right? It's people looking at the sky through telescopes and trying to see what's there and how bodies behave, how things move around in the sky. And then it's also people looking at blackboards and pieces of paper and calculations and notebooks. And so a lot of what we knew about black holes in the early period came from that latter group of people, right? There really wasn't anything in the sky to look at. But eventually there was, right? Eventually you could start to see things move as though there must be something else there. Is that fair to say?
Yes. Astronomers learned how to measure velocities of stars moving around centers of galaxies, and they found that the stars were moving so fast, indicating that the gravitational field near the center of the galaxy was so strong, and the center occupied quite small, well, relatively small region of space, then the center of a galaxy must be a black hole. The radius and mass of the central region of a galaxy is in the linear relation, which was discovered by Schwarzschild. By the way, I have to say some interesting factoid. The formula between mass and radius of the black hole derived by Mitchell and Laplace using Newtonian gravity, so using the wrong formalism, and the formula derived by Schwarzschild are identical. It is beautiful coincidence.
Huh. Yeah. So Marcia, one of the senses that I have, and boy, I'm slowly or maybe even rapidly moving out of my depth. I think I'm caught in my own event horizon, being dragged into the huge black hole of my ignorance. But my sense is that there's this kind of odd game of ping pong that almost sort of starts up. I mean, this is initially something that's true because it's mathematically true, because what we know about the laws of the universe and then the math that goes along with them suggests that it must be true. And so there's some push and pull against that, and there's some scientists who basically say it can't. We don't care. It can't be true. It can't be true. And then, when some of the things that Nicodem is talking about, things that can be seen later that suggest the truth of the black hole, then it's almost as though the arrow points a little bit in the other direction. How many mathematical truths are actually challenged? How many former mathematical certainties are challenged by the truth of black holes, right? Some closely held beliefs are kind of put into play in a different way. I don't know. Am I making any sense at all?
Well, that's true. At any time in physics or mathematics, when you have what they call a singularity, and in this case, you have a point with infinite density but zero volume, well, in mathematics, that's usually a sign that the physics equations you're working with are failing in some way, that there has to be another solution. This happened with quantum mechanics. There were certain experiments carried out, and they were failing with the known rules of electromagnetism and radiation. And Max Planck in 1900 came up with this scheme called the quantum in order to explain it, and that opened up a whole new field. So the singularity that he had to deal with led to a whole new field of physics. And many people in physics think the same about the black hole, that the singularity they're facing there at the center is really a sign that we need further mathematics, further models to truly understand what's happening there, to explain the physics.
All right. Well, we're not going to solve all these things in the course of a 49-minute radio show, but we're going to tell you what we can about two really interesting conversations that are going on. One of them comes from Nicodem, our guest here, and the other one is coming very recently from Stephen Hawking. So why don't we take a break? We'll come back and we'll bring you up to date on that. I love that we're talking about black holes, and there's a promo for Teilhard de Chardin, who was sort of on the spiritual end of that conversation. All right, well, we're not going to do that right now. In just a minute or two, we're going to tell you very specifically, Marcia's going to tell you in particular about Stephen Hawking and the role that he's played in this, and Marcia and Nicodem will tell you also a little bit about what's going on right now, about the conversations that have been had in Stockholm recently, which perhaps portend a change in thinking about one part of a black hole. But as long as we've got Nicodem Popławski here, a theoretical physicist, senior lecturer, and physics coordinator at the University of New Haven, and sometimes mentioned as the next Einstein, we'd be fools not to find out what he's thinking about black holes. And what you're thinking about black holes is pretty different from some of the conventional notions of a black hole as kind of a dead end, right? And that, eventually everything sort of collapses down to the space of infinite gravity, infinite density, taking up no actual physical space in the universe, and that's that. It's over. Game ends. That's not quite how you see it right now, right? Yeah.
What I think is that black holes are spherical doorways to new universes. It is like a Doctor Who show when you can enter the police box and you are inside and you realize that you are in something larger than the police box. And so, as Marcia said, singularity indicates that our understanding of gravity is not complete. But in 1920, Elie Cartan, a mathematician, he wanted to add to general theory of relativity by Albert Einstein the concept of spin. So particles can rotate, so they have something which we called angular momentum. But in 1920s, physicists discovered that elementary particles have spin, which is like they behave as if they were rotating, although they are not rotating. And this is quantum mechanical property. And Elie Cartan found that if you add spin of particles to gravity, then the space-time is not only curved, like Einstein said, it's also twisted. That's called torsion. And then in 1960, Kibble and Sciama. By the way, Tom Kibble is one of the 6 people who discovered Higgs mechanism. So Kibble and Sciama discovered that that spin and torsion at extremely high densities, torsion only exists at extremely high densities where we need to cure gravity. They discovered that torsion acts like a gravitational repulsion, which means when the matter inside a black hole wants to collapse to a point, at extremely high densities, just before the matter otherwise would create a singularity, the torsion says no. So the matter does not reach the singularity, the collapse stops, and then the matter wants to expand back. But the thing is that it cannot go back through the event horizon, so it has to go somewhere else. So it creates a new branch of space-time. It creates new universe on I would not say inside, but on the other side of event horizon.
Well, that would suggest that where we are right now is what came from and is the other side of something else that was before, right? Is that possible?
Yes, this would suggest that our universe was formed as the other side was formed on the other side of a black hole existing in a parent universe. Now, the problem is only where the matter came from, because mass of our universe is, of course, much larger than the mass of the black hole, which formed our universe. But the production of the mass came at the beginning of our universe through gravitational quantum production of particles, and the Big Bang actually should be called a big bounce, because the matter was collapsing, stopped, a lot of new matter was produced, and the universe bounced and started expanding as the new universe.
All right, so this is a pretty radical idea, and maybe we can circle back to it and just sort of talk about how radical ideas are received. New ideas are received in the study of all this. We've all been to the movies and seen Theory of Everything and seen Stephen Hawking essentially be kind of shouted down about his original ideas. So Marcia Bartusiak, with that in mind, once again, her book is Black Hole, How an Idea Abandoned by Newtonians, Hated by Einstein, and Gambled on by Hawking became loved. I mean, we're now at the point, and you listen to Nicodem, we're now at the point of discussing and maybe arguing about what black holes really are, how they behave, whether they're finite, whether information is totally devoured by them. But we're not at the point anymore of discussing whether there are such things as black holes. So when was that? When was the tipping point on that? When did black holes become accepted science?
I think it started in the 1970s, especially with X-ray astronomy. The thing about black holes is they do have such a gravitational field that they attract matter that's close by. Say if a black hole is paired in a binary star system with another star, a big star with an atmosphere, it will draw off that matter and it will spiral around because it doesn't just suddenly go into the black hole. It's like a traffic jam. It takes a while. And so like a little whirlpool going around the hole, the matter collects, and as it's swirling around, getting ready to fall into the hole, it gets really energized to tremendous energies. And they are especially brilliant in X-rays. And X-ray astronomy didn't come about until the 1970s. And that is when they started seeing these particularly bright X-ray objects in the sky. One in particular called Cygnus X1 that they worked out the orbital mechanics and determined that this particular unseen star that seemed to be putting out X-rays was at least more than 10 solar masses. That put it into the black hole zone. And since then, the astronomers have gotten ever better observations, and now they are totally accepted as normal denizens of the cosmos. You have regular stars, you have neutron stars, and you have black holes. Not only stellar-sized black holes, normal black holes from the collapse of an old star, but as pointed out earlier, supermassive black holes at the center of each and every major galaxy in the universe. It may be that they're even important in the creation of a galaxy. Our very life may have depended on the formation of a supermassive black hole in a galaxy.
Right. You absolutely just went where I was going to go, but that's great. So, Nicodem, when I listened to your theory, I was thinking about that. I was thinking because, once again, I'm dimly aware of what she just said, that the notion that supermassive black holes seem to exist at the center of galaxies it's kind of a new face on black holes, right? The notion that maybe they're not just destructive things, that maybe they're creative things. And that kind of fits with what you're talking about, right?
Yes, when I think about black holes and universes, I imagine our universe having like billions of galaxies. Each galaxy has a supermassive black hole, and if black holes really form new universes, so looks like our universe has billions of babies, basically, which are formed through black holes, and then this cosmic procreation can just happen forever. So the black holes are good. And actually, there's also one thing about supermassive black holes. They are much less dangerous than small black holes, because if you would like to go through a small black hole, then the tidal forces at the event horizon are strong. So there is a process called spaghettification. Objects get destroyed, they get stretched. But if you go through a supermassive black hole, you even won't notice that you go through an event horizon. The tidal forces are very weak.
Yeah, and not as hot, right?
Yeah.
Supermassive black holes would be presumably cooler.
Yeah.
So, Marcia Bartusiak, first of all, what would Einstein think about the conversation we're having right now? Would he be okay with it?
This is interesting. I'm of two minds of this. Someone else asked me this question. And on the one hand, Einstein really didn't like the idea of this at the time. He didn't think of it as a black hole. He died before that full concept came into play. He called it the Schwarzschild singularity. And just that idea of having an infinite density in zero volume bothered him terrifically, because he knew that was usually a sign that more physics needed to be done. So he really didn't like the idea of the singularity. But on the other hand, he also had a theory about the model of the universe, which was a spherical universe that was stable and serene. And when it was discovered by Edwin Hubble and others that the universe indeed was not like that it was expanding and growing, he at first did not like that idea, but he visited Mount Wilson, went up to the mountain, heard the data, saw the astronomical data, and came down off the mountain and said that Hubble had smashed his theory with a hammer. So he, as a physicist, respected evidence. So there's another part of me that thinks he would look at the astronomical evidence and probably agree that there are these unusual objects. They do exist, but we still don't fully understand what exactly is happening inside.
As long as we're talking about Einstein, Nicodem Popławski, the first time somebody showed you the magazine article where you're described as one of the possible next Einsteins, how did that feel? I assume he's a hero.
Well, he's my hero. Well, my colleagues asked me the same question, how did it feel? I answered that, well, I cannot be Einstein because I will never had such a strong facial hair as he had. So, but, well, I felt happy because Einstein is my hero because he revolutionized our understanding of physics, and he was like thinking in terms of like very simple thinking experiments. How does it feel to travel on light, or can we do this or not? And like a lot of mathematics he did, like for special relativity. It is on quite simple level. It can be taught in high school. However, he was he was brave to do that because no one else before him. Although Lorentz did a lot of mathematics of special relativity, but from different assumptions. So Einstein was very brave, and that's why he's my hero for this reason.
Okay, I'm going to both have you talk a little bit about what's going on in Stockholm or what's going on with Stephen Hawking right now. Maybe before I ask Nicodem to explain what's happening right now with the information paradox, which is the thing that Hawking's having a conversation about right now, maybe, Marcia, you could remind us, those of us who saw the movie or read the book, maybe you can remind us sort of where Hawking had taken us to so far. What's in what you've written about, and we should say that your book is really about the history of the idea as opposed to a physicist's explanation of the idea. So in the history of the idea, of this idea of the black hole, what was Hawking's significance so far?
It was a very significant step. I still think of it as his greatest work, which happened very early on in his professional career in 1974. You know, we talk about a black hole, and when we see it in the movies, it's the classical version of the black hole, that deep, dark pit in space-time that will swallow everything and not give anything back. But that is based solely on Einstein's theory of gravity, of general relativity. What Hawking did in the 1970s was suddenly look at the black hole through a different lens. He applied the laws of quantum mechanics. He looked at the black hole from the submicroscopic level and says, what does the black hole look like there? And what he discovered is the black hole ain't so black, as he put it. He discovered that over long periods of time, the black hole actually radiates. It gives particles out and shrinks over time. Now, for a stellar-sized hole, that would take an immense amount of time, 10 to the 67 years. I mean, that's a 1 with 67 zeros, so it really doesn't affect us in our everyday life. But it did show that the black hole was not this classical entity that comes out of Einstein's equations, but something else altogether on the atomic level. In fact, after time goes by, the black hole will shrink faster and faster and faster until it will explode in a giant fireworks of radiation and energy.
All right. So one of the things that became an interesting conversation this week, I guess controversy would be the wrong way to put it, but it's certainly Hawking putting a new, you should pardon the expression, spin on some of his thinking. He was looking at the question of what's called the information paradox. This is something that continues to puzzle scientists who study black holes. So, Nicodem, I'm sure you followed all this and what Hawking said last week. What was he saying?
Stephen Hawking proposed last week a theory that the information is not lost, or because before that, I think the conventional thinking was that when the black hole evaporates and radiates, then information is lost in this process. Hawking proposed that information never goes to a black hole, but it's somehow frozen on the event horizon, stored at the event horizon. Now, I'm waiting for a paper to come out probably within the next month, as he said, because right now I was just watching the media, so that's what I learned. And I have to say, I agree with this. I agree with this because in our frame of reference, black holes don't exist. They are almost there. The matter which goes to a black hole is approaching a black hole in an infinite time, so does the information. So he's correct in our frame of reference. Now, what happens in the frame of reference of the information traveling through event horizon, I do not know, and I'm waiting for the paper,
right,
so I could judge.
Well, first of all, when we say information, we're talking about sort of what was the star, right? The everything that was the star that became the black hole. That's the information?
Yes, like because black holes can be formed from different varieties of stars, but when the black hole is formed, it is described only by 3 numbers. It's very simple. Those numbers are the mass of a black hole, its angular momentum, and its total electric charge. This quantity is usually not very important. Usually they are neutral, approximately. So, but only 3 numbers. So there was a lot of information before, and now we have only 3 numbers.
Mm-hmm.
So the information is lost quite a lot.
Although as a Popowskian, wouldn't I believe that it just comes out on the other side, right? It comes out in the next universe.
This is what I would propose. It goes to the other universe. Nothing is lost.
Yeah, so we don't even have to worry about Hawking's problem. We already know where it's going.
And the worry of the loss comes from the universal thought of the conservation of mass and energy, which is a foundation of physics. So when they talk about lost information, they're worried about the very foundation of physics.
Right. So, all right. First, my big takeaway so far is that whenever this kind of thing comes up, I'm going to say that I'm a Popowskian, and I know what happens to this stuff. All right, so we're going to take a break. We're going to talk about then what your popular understanding of black holes has been and who's decided whether it was right or wrong.
Scary. Don't worry, black holes aren't evil. They don't purposely destroy planets or people. You've been watching too many sci-fi movies. When you learn about them, black holes aren't scary. The sun's gravity makes the planets go around. The Earth's gravity keeps us all on the ground. Black hole gravity does the same thing. Trade one for the sun and everything's the same.
The study of black holes can unlock one of the greatest mysteries in our universe. Why is Donald Trump popular? Wait, I misread that. It's the study of jackholes. Today's show was produced by Lydia Brown and me, Kyone Wolf. Our interns are Dan Schultz and Sarah Flaherty. Greg Hill appeared in the intro and tweets for us at WNPR Colin. For show pages, articles, and videos of the Faith Middleton Show staff making black hole lettuce and tomato sandwiches, visit our website, WNPR.org/Colin. On tomorrow's Nose, is Donald Trump a black hole pulling the lunatic fringe toward the center? And now, back to Colin.
That's so true about the Faith Middleton Show staff. If they can't make a sandwich out of it, they're not that interested. So we are talking about black holes today. With us, Marcia Bartusiak. She is the author of Black Hole, How an Idea Abandoned by Newtonians, Hated by Einstein, and Gambled On by Hawking Became Loved. Nikodem Popowski, a senior lecturer and a physics coordinator at the University of New Haven, sometimes referred to as one of the possible next Einsteins. He's on the short list. And joining us now also by phone is Andrei Bormanis. He has worked as a writer, producer, and science advisor for several Star Trek series and feature films. So, I was saying before, Marcia Bartusiak, reading your book today, and by the way, really, if all of this stuff kind of just slides through your fingers and you really have a hard time grasping it, this book is like 180 pages or something? I mean, it's not very long, and it will give you some kind of a handle on it. I started to understand it better. And as I was reading it, one part of it, this isn't so much about black holes as it is about just sort of the development of general relativity and Einsteinian physics. I suddenly thought, wow, I've heard this before somewhere. Where was it? Where was it that I encountered this recently? It was somewhere in popular culture. And then I remembered, oddly enough, was on the program Masters of Sex, which is about Masters and Johnson, the sex researchers of the 50s and the 60s. There's a scene in there in which Bill Masters is facing a group of his colleagues about his research, which has just become unveiled. It's very controversial research, even in the scientific and medical communities. And one of his colleagues at this, it's at the end of a dinner, a big annual dinner at some hospital or something, asks him a question about in all this research about sex, he's not talking at all about love. So where's the love? How come he's not talking about love? Let's hear the rest of the clip.
My question, Dr. Masters, is where is the love?
In 1687, Sir Isaac Newton discovered what was then known as the law of universal gravitation, gravity. Take two objects. The larger object exerts an attractive force on the smaller object, pulling it towards itself, as it were. An apple falls from a tree. The Earth, by far the more massive object, pulls the apple to the ground. Simple enough. Only Newton's theory left scientists a rather puzzling problem. To paraphrase you, Dr. Farber, where is the gravity? It's not something you can see or touch. It's not something you can put under microscopes or examine from a telescope. Well, 230 years after Newton, a German patent clerk in Switzerland finally realized that scientists have been asking the wrong question all along. They would never find an object in all the immensity of space called gravity because, in point of fact, gravity is nothing but the shape of space itself. That clerk, Einstein, posited that the apple does not fall to the ground because the earth exerts some mysterious kind of force upon it. The apple falls to the ground because it is following the lines and grooves that gravity has carved into space.
And then he goes on to talk about how, in his analogy, love is like that. That you can't see love, but love is the curvature, I think he says, of our desire. So, Marcia Bartusiak, maybe not a perfect explanation of Einstein and general relativity, but there's popular culture in what I thought was a pretty exquisite analogy, anyway.
That was actually very well done for a popular show like that.
Yeah, as I was reading your book today, that's why I was thinking, where did I read this almost exact same thing recently? Well, we want to talk a little bit about how this comes up, how it looks in popular culture. And so we are adding to the conversation Andrei Bormanis. He's worked, as I said, as a writer, producer, and science advisor for several Star Trek series. First of all, I have to ask, first of all, welcome to the show, welcome to the conversation. And I have to ask, how did you get involved? How does one come to be the science advisor to Star Trek?
Well, that's a long and interesting story, but the compressed version is that I was a physics and astronomy major in college. I had some aspirations to write. I took creative writing classes, wrote some scripts. I got a NASA fellowship to go to graduate school at George Washington University, and while I was there, I was trying to arrange a meeting to go pitch some story ideas that I'd come up with for the show Star Trek: The Next Generation, which was on at the time. And I managed to find an agent who could set up such a meeting, and in the process of trying to do that, she found out that they needed a new science consultant, and they wanted somebody with both a science background and a creative writing background, somebody who knew the show and who knew how to read a script. And I had no idea that they even had a science consultant on the show, but was happy to hear that guy had been promoted to the writing staff and they were looking for a replacement. And they interviewed me, they liked me, and they hired me. And so in May of 1993, I moved from Washington, D.C. to Los Angeles to come and take on that job.
Today we were talking about black holes. Long before you arrived on the scene, Star Trek, which always did pride itself on having some scientific grounding in what it was talking about, probably had the first black hole representation on television. Almost certainly did around 1966 when I was watching Star Trek as a kid. And I think the term black hole wasn't even in currency at the time. It wasn't even in circulation. So I think they called it a black star.
They called it a black star, and I think today, and obviously your other guests would be better at answering this question than I, but in today's world, I think that there is a distinction between a black star and a black hole. Back in the 60s, I think that those terms were probably more or less interchangeable. But the interesting thing about that story, which, as you said, was in 1966, is that the Starship Enterprise, cruising along in interstellar space, was caught off guard by the gravitational pull of this object, which they couldn't see on their sensors. And because, of course, the Starship Enterprise can travel faster than the speed of light, it can escape the gravity of a black hole even if it's crossed the event horizon. And unfortunately, by doing that and putting the warp drive in reverse, I think they said on the show, they ended up traveling backward in time. And I thought that's also pretty sophisticated understanding of the relationship between space-time and how black holes could, in some capacity, actually serve as time machines. So it was pretty prescient on the part of writers of that particular episode.
I want to ask Nikodem Popławski, I don't know, can you watch science fiction movies? Can you watch science fiction television? Or do you have to get up out of your seat and walk out because the physics aren't right? Or
I love Star Trek. I watched a lot, almost all the series. So, and when I watch Star Trek, I don't think as a critic, like to find the mistakes or something. I just want to have fun. But then after the show, of course, like I talk to my friends that, well, by the way, one thing there was not quite right, right? So, for example, now, about the episode traveling backwards in time, like actually time is one of the greatest mysteries, even like for me, because like Einstein said, time is just a coordinate. But for example, why time goes like from past to the future, and we cannot go backwards in time? And this is like a mystery, because so maybe we can. For example, antimatter can be thought as matter traveling backwards in time and viewed in a three-dimensional mirror. So physicists can make like a lot of concepts, but so I don't think we understand completely the concept of time yet.
Right, and we're going to get Ron Mallett back in here to help us out with going backwards in time. Andrei Bormanis, first of all, we are going to run out of time here pretty quickly, speaking about time, but so you've dealt with black holes in your role as consultant, and I think you've also now become a writer for Star Trek. So how have you used black holes fictionally?
In my original stories, I've never actually invoked a black hole, in the plot, but I've had to deal with them as the science consultant on Star Trek. On more than one occasion, both black holes and wormholes. A wormhole had a prominent role in the series Deep Space Nine, which I worked on as well. It was a feature of that particular universe that they had a black hole, a wormhole, that allowed a starship to traverse something like 50,000 light years in 30 seconds time. And one of our writers had commented that there's this sort of story that the Inuit people who live up in the Arctic have 100 different words for snow, and on Star Trek we had 100 different words for black holes and wormholes. We would call them quantum singularities class 4 or temporal schisms and this, that, and the other, basically to mask our ignorance. And we had an episode early in the run of Star Trek Voyager called Parallax, and in that episode, the Starship Voyager encountered something that we called like a class 4 quantum singularity, because we didn't want to say black hole, because I knew, and I think the writers knew, what you're describing here is not really the way that a black hole would be expected to work. So let's call it something else, and sort of tantalize the audience with the idea that there may be many different varieties of these phenomena, of where gravity is warping space in an almost infinite sort of way. And that episode then, took a lot of license with the concepts that we typically talk about when we're talking about black holes. And it made for an interesting story. I'm not sure it was a terribly satisfying story on a science level, but it opened up, the mind of the audience to the idea that there are these exotic things in space that, if we could get close enough to them, might affect our perception of time, might affect our perception of our location, and maybe even allow us to be in two places at once, in a sense.
I wish I could move time around so that we had more of it right now. This has been a fascinating conversation. Andrei Bormanis, great to have you. Nikodem Popławski, I am now officially a Popławskian astrophysicist. Marcia Bartusiak, it's a great book, The Black Hole Book. And thanks to everybody else who helped out today.
Thank you.
When I wake up, I'll be inside my daughter's bookcase. I guess that doesn't really happen with black holes. I hated that movie anyway. All right, we'll be back tomorrow with the news.
Captain Wolf, I think that's a black hole ahead.
Really? I mean, looks kind of dark blue.
No, are you kidding me? That's a black hole.
It could be like a royal purple.
Captain Wolf, I'm telling you, it's a black hole. I know a black hole when I see one. We've got to change course.
Calm down, Lieutenant Hill. Color is subjective. Black, yellow.